Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to look at a forced oscillation for a second order differential equation. And so here's what we're going to do and not only that, we're going to find the rectangular solution and then the polar solution and then look at an example. So the problem is we're going to solve y double prime plus by prime plus cy equals cosine of omega t. Cosine omega t. And remember, we could solve this using the exponential, using a complex number, but we're going to take a look at it today. Well, what if you forgot that? And what does the rectangular solution and the polar solution tell us? So let's try it that way. So our general solution was our particular solution is we're going to do this. We're going to try y particular is m cosine omega t plus n sine omega t. And remember this. Remember that even though our driving force is a cosine, the reason why the particular solution can't be simply a cosine is that as soon as you take a derivative of a cosine, you introduce a sine. And so you could take a derivative of cosine and get back to sine, or the sine and get to cosine. You'd have like terms here, but not here. So in other words, we need both the cosine and the sine, some combination of them, into our final solution so that all of our like terms are going to simplify to a cosine. So in order to do this, we're going to take our particular solution, we're going to substitute it into our differential equation. So I need my y particular, and in order to do that, I'll need y particular prime. So here we go. Let's take the derivative of this. The derivative of cosine is going to be a minus sine. And the chain rule, I'm going to pick up an omega. So I'm going to have a minus m omega sine omega t plus, the cosine is going to give me a cosine plus, so I'm going to have an n. The chain rule will pick up omega cosine omega t, cosine omega t. And then let's take our second derivative. We're going to need that as well. So I'm going to have y particular double prime is going to be equal to, my sine will become a cosine, and I'll still have a minus, and I'm going to pick up an omega. So I'm going to have a minus m omega squared cosine omega t. Plus, this is going to be a minus now. The cosine, derivative of cosine is minus sine minus n omega squared sine omega t. Okay, there we go. Now, our solution, we could plug all this in. It'll take the entire blackboard space, or we can just do this very carefully. We can pick our way through. So we're going to pick our way through. And what we're going to do is, the solution notice, let's go back here. If I look at my original solution, I have cosine, I have one cosine, and I have 0 sine. So that's how we're going to solve this problem. We're just going to figure that all the cosines on here need to add to 1 cosine here. All the sines on the left-hand side need to match up to 0 sines on the right-hand side. So let's write this as, so let's work on our cosines first. Cosines. All right, here we go. Let's look at y double prime. So y double prime is going to pick up an a times a minus m omega squared. So minus a times oops, I wrote that. Let me change that order. Be consistent. Minus m a omega squared plus, okay, now we're looking for cosines in my first derivative. I've got a cosine right here, but it's going to be multiplied by the b, so that's going to be plus n times b omega, and then we go back to plus cosines from the y particular. It's going to be multiplied by c, so I'm going to get c m. I'm going to write the other way, plus m times c, and since these are cosines, we're going to pick up one cosine. Okay, we're going to do the same with sines. Sine. So for our sines, let's see what we've got. Sines. Okay, let's start with our second derivative. So our second derivative, I'm going to pick up an a minus an omega squared minus, we can rearrange the order, minus an omega squared. And then we go back to our first derivative. I've got a b times y prime, so that's going to be minus b times m times omega minus b times an m times an omega. And then y particular, I'm going to have a c times n plus c times n. And that's going to give me 0. Let's do a little bit of cleanup. Let me do a little cleanup. So I'm going to clean it up again by cosines. Notice that I'm going to be working, let me think about that for a second. Hang on a second. Oh, goodness gracious. How in the world did I not see that? So let's regroup these by m's. So I'm going to factor this out because remember what we're trying to do is, these are big problems. It's easy to get lost. We're going to be solving for m and n. We need to find these coefficients. So I'm going to factor these by m's. So let's write this as m, working on the cosines. So I'm going to take it by m's. I have a c minus a omega squared. A omega squared plus n times b omega equals 1. Okay, now we're booking. Sines. Let's do this again. Sines. What do I have here? M's. The m's, I don't have a lot. I have an m here. So let's write that as m times minus b. Actually, I'm going to write it this way. Minus m times b omega plus n times n. When I factor, here's my n terms. That's going to give me a c minus a omega squared. C minus a omega squared equals 0. Okay. I think we've got it. I'm going to do one more thing. I'm going to call this equation 1. And I'm going to call the second one equation 2. There's a few different ways that you could work through this. I'm going to follow the same way our author did it, just so you can kind of see what the writing and the working of it. What we're going to multiply, the equation 1, I'm going to multiply through by c minus a omega squared, and equation 2, I'm going to multiply through by b omega. And so let's do that. So I'm going to take equation 1, I'm going to multiply it by c minus a omega squared, and the second equation times b omega. And then we'll subtract. So here we go. And I'm going to call these results equation 3 and equation 4. So I'm going to have m parenthesis c minus a omega squared plus n times b omega times a minus, c minus a omega squared is equal to c minus a omega squared. Okay, there's equation 3. Equation 4, this is going to be a minus m times b omega times, oh goodness, I'm multiplying it by b omega. So let's just square that. Oh, this just gets better by the moment. Squared plus, then I'm going to have an n times a b omega times a c minus a omega squared. Oh, look at that. And that's just 0. Oh, this worked out nicely, because what I'm going to do is I'm going to take equation 3 and I'm going to subtract from it equation 4, and we'll put our new result right here. Well, when I subtract this term, let's just go term by term. So this term minus this term is going to give me an m of c minus a omega squared plus m times b omega squared equals, then this one, the c minus a omega squared minus 0 is going to be c minus a omega squared. Oh, there. Our next step is we're going to factor in m. So I have m times parenthesis, big parenthesis here, c minus a omega squared plus b omega squared is equal to c minus a omega. And so there's m. M's right there. M equals c minus a omega, all of that over all this big factor here, c minus a omega squared plus b omega squared. There's m. That's m. We're almost there. I'm going to do this. Let's substitute m into my initial reaction is we've got a 0 here. Zeros tend to just save me one less thing to do. So I'm going to put my m into equation. Oh goodness, no. Let's go, it's even easier. Let's put it into equation 2 right there. Into equation 2. So m is going minus an m. Oh my. Minus c minus a omega squared times b omega. All of that is over our denominator, c minus a omega squared, plus b omega squared oh dear, plus n, oh, I see it. This is going to work out nice. C minus A omega squared is 0. We're going to move this term over to the other side. Did I make a mistake? Where? Here. Oh, there. Thank you. Yes. Oh, I've got a great filming crew here. N, we're going to move this term over to the other side. So I have N times C minus A omega squared equals C minus A omega squared B omega over this denominator, C minus A omega squared plus B omega squared. Oh my, look at that. These are going to cancel. These are going to cancel. And canceling is best done in orange. Look at that. Oh, that's just so much nice work. And there we have it. There's N. Let's write those. Let's write that right here. I have, but before I do that, I'm going to do one more thing. I'm going to use the capital D. I'm going to use a capital D. And notice here, the denominator in both N and M are the same. So let's let D equal A minus, C minus A omega squared plus B omega squared. If we do that, watch how nicely these work out. M is now C minus A omega squared over D and N is equal to B omega over D. I think I got all of those terms. We do. There's my B over omega over D. Okay, we've got that. Now, okay, if I write this, y particular, and I'm just going to write this out one more time, equals C minus A omega squared over D cosine of omega t plus the n, this is B omega over D sine omega t. Okay. This would be rectangular form first called, this is called rectangular form. Rectangular form for our particular solution. Okay, now we're going to take this, and remember that differential equations are often then written in just cosine. And remember, our input was simply in just cosine. And so if we take from our rectangular form, and then what we want to do is write it in just cosine, we'd call that polar form. So that's our next thing we're going to do is we're going to write the rectangular form rectangular form in, that's tight. write it in polar form. Polar form. I think I did my board work backwards, but that's okay. We'll just have to make do. Polar form. Okay, here we go. Now, these are things we've done in our previous sessions, and what we said is this. The polar form would be y particular is equal to some g, some capital G, this is our gain, times cosine of omega t minus alpha, where this is some kind of a shift. And we worked out that this is, the gain is equal to the square root of m squared plus n squared. Now, we're gonna solve this. We're gonna solve this, but I'm gonna work with g squared for a moment, and then we'll come back to g. So if I take m, that's right, we're gonna take all of m and we're gonna square it. So let's do that. Oh boy, m, that is c minus a omega squared over d. We're going to square all that. So I'm going to just write it this way, squared and squared, plus n, well that's b over, let's write it this way, n is b omega over d. And then we're going to square it, so I need to square my numerator and my denominator. But look at how nicely this works. I've already got a common denominator. But c minus a omega squared plus b omega squared, whoa, that's right there. That's just d. It's right here. It's all that work we've been doing. So the g squared is, in other words, this is d over d squared. That's just 1 over d. Wow, that cleaned up so nicely that we can clean this up as g is equal to the square root of 1 over d, and it's even nicer if we just write it as 1 over square root of d. Okay, our last bit is alpha. We need to find alpha. I'm going to need all these formulas here. I'm going to come over here. So our alpha, remember what we said is we said that the tangent of alpha is, well, if you think tangents, it's the sine, it's the opposite over the adjacent. Our opposite piece in a rectangular coordinate is the sine. Well, sine was our n coefficient, and the cosine, or the adjacent sine, was our m. It's associated with the cosine. Well, if we solve this, this is n, that's b omega over d, over, that's a big fraction here, over c minus a omega squared over c minus.
Why don't we just cut it there? Why don't you just stop it there? Yeah.
All right, let's simplify this. This is, I'll write it out. This is b omega over d times, you flip and multiply, d over c minus a omega squared. We can write this as b. So you can say our tangent of alpha is b omega over c minus a omega squared. Now, wow, here we go. Let's try this. Solve. So let's solve y double prime plus y prime plus 2y equals cosine. Oh, you know what? How about cosine t? Let's just do that, cosine of t. Very specific example, and there's actually a bit behind this. Now, if you forget all these formulas, which most of us will, you can always go all the way back and just start working through the process. And you can find your rectangular coordinates. I'm going to use my formulas because we've spent all this time coming up with them. So let's write out what we've got. We've got A, that's right here, that's 1. B is the coefficient on the y prime, that's 1. C is the coefficient on the y. And omega, it's tucked inside there, our omega is also 1. Lots of 1s and 2s. So let's do some calculations. We got a few calculations to do. Let's try, our first one is, let's find D. D, come over here, all the way back here. D is this. It's C minus A omega squared squared plus B omega quantity squared. A, here we go, we're going to do this all at once. C is 2. Minus A is 1 times omega, that's 1. Square it, it's still 1. And square that. Plus B, that's a 1. Times omega, that's also a 1. And we square that. Let's see. 2 minus 1 is 1. Squared is 1. 1. Oh, look at that. D is 2. And so now we can find M. Oh my, it gets even better. We've already done the calculation. C minus A omega, that's that. That's 1. D is 2. N is B times omega. That's this little piece. We'd found that. D is still 2. There we go. So a rectangular solution, right? So let me write that, a rectangular solution. Rectangular solution is y particular is 1/2 cosine t plus 1/2 sine t. Okay. Let's look at our polar form, and you'll see why it's so important. If there's one form you really need, this is it. And here's why. Notice, polar has the form of g cosine omega t minus alpha. G is 1 over the square root of d. D is 2. 1 over square root of 2. We know omega is 1. Alpha is the tricky one, but not so bad. That's just the tangent of alpha is equal to, it's right here. It's B omega. B omega we calculated here. That's 1 times 1. And then our denominator is C minus A omega squared. That's this piece here. That's also 1. So tangent of alpha is just 1. That's alpha is pi over 4. And there we got it. It's all there. So we can say in polar form, our y particular is 1 over square root of 2 cosine omega is 1, t minus pi over 4. Now, what does this tell us? I want to show you, and the only way to show you is with graphing. So I have some beautiful colors here, yellow and blue. And what I want to do is look at this. Let's make up a graph. I'll try to be pretty accurate. It'll help us. Okay, so that's pi over 2. Pi, 3 pi over 2, and there's 2 pi. And let's just graph cosine. I'll show you why. Why would I graph cosine? The reason for just graphing cosine is cosine was the input to my, I have some kind of a system here, and I'm forcing it by cosine of t. The cosine of t, I'm going to graph it, it's going to be 0, 1, let's, down here, minus 0, I think, oh goodness, 1 pi over 2 pi, 3 pi over 2. Oh, there we go. There's cosine. So the cosine is this. There's my cosine. This is the input onto our system. But look at what our solution says. That's what's so amazing. The solution says our amplitude is not 1 anymore. It got smaller. You could think of this as root 2 over 2. Square root of 2 is about 1.4 divided in half. It's about 0.7. So that's right there. That's probably precisely 1 over the square root of 2. So if I go there, we'll drop down here. There's minus 1 over root 2. Here, but now this is a shift of the cosine function. So it doesn't start at 0. It's shifted by pi over 4. So now I'm going to have my shifts. It's going to start right in the middle there. So let's see if I was to graph this. It would be right in the middle of all of those. So now it's going to start, oh, but it got reduced. So now it starts here, comes down to here. I'm at the bottom over here. Everything is shifting to the right now by pi over 4. So my response is the yellow. This is the output or the response to the input. And what does that cause from? It's caused from our damping coefficient right there. I hope that helps. Thanks for watching.